Hello everyone, my name is Dumb Engineer. As you all know, I demystify tricky data science and data engineering concepts through captivating storytelling, and I'm here to tell you another story today. Have you ever heard of the term MAP? If you've not, don't worry. Today I'm going to tell you a story. In fact, my story will be so interesting that by the time I am done, you understand the concept of MAP so clearly that you can explain it to a child. So let's get cracking. So let's imagine a particular computer vision system as a detective. Now the job of that detective is to look at an image and answer a question like, is this a cat or a dog? But here's the problem. Images can be messy. Lightnings in images may change, they are rarely consistent. Angles may change. Noise may exist in any image. So the computer never sees perfect data, it only sees cues. The detective first looks at the evidence. In computer vision, this is called likelihood. For example, if this were a cat, how likely will it be that the image will look like this? Or if this were to be a dog, how likely will it be that the image will look like this? Our detective now checks for patterns. Patterns like the fur texture, the shape of the ears, ages and colors. This is the data-driven part of the decision. But relying only on evidences such as this can be dangerous. So if that is the case, what then happens? Now, the detective asks another question. What do I already know? This is what is known as prior. For example, if the image comes from a wildlife camera, probably in a city, we know that in cities, cats are common, tigers are not. Even if the image kind of looks like a tiger, the detective knows I almost never see tigers around this area. This knowledge really matters. In computer vision, priors represent what the model believes before seeing the image. It is at this point that the detective makes his final and most important move, MAP. MAP asks one simple question. Given the evidence and what I already know, what is the most likely explanation? In other words, combine the likelihood with the prior, then choose the answer with the highest posterior probability. In fact, that is why it is called maximum a priori. Think of it as a strategic way of guessing smartly, balancing what the model sees and what it expects. So a question you may ask is, why then does MAP matter in computer vision? MAP helps models to be more stable with noisy data, avoid unlikely predictions, and also use real-world context. For example, in night images, priors help complement for low visibility. In medical scans, priors help reduce false alarms. In tracking objects, priors help predict where things move next. Without MAP, systems should be overly confident on bad data. So, the next time your phone unlocks using your face or your expensive self-driving car recognizes a pedestrian, remember, key system is not just seeing, it is balancing evidence and belief. That is the power of MAP.